Okay, today we will show the software design. Software design deals with transforming the customer requirements as described in the SRS into a form that is implementable using a programming language. Okay, so software design কি করে, it converts the SRS what is written English like written form, it is describing form, and converts it into a graphical notation type language, and that notation may be implemented by some programming language or some that graphical notation can be drawn using some tools, software tools. Okay, we can broadly classify the design activities into two parts, the preliminary parts and the detailed parts. Preliminary parts we called a high level design, and then the detailed design. So before going to the details, what is achieved during the design phase? The transformation of SRS document to design document is the achievement of this design phase. A form easily implementable in some programming language. So we will make a form which form can be easily implementable to some programming language. And this SRS document, this is confirmed through the design activities into some design documents. So item designed during design phase. The module structure, the control relationships among the modules called relationships or invocation relationships, and the interface among different modules. So first we have to find out what is the module of the total system. We have to find out all the modules. After getting the modules, we will find out the control relationship among the modules. What are the relationships between these modules? And then what are the interface of these modules? And what are the data will be exchanged their values from one module to another module. So these are the steps of this item design phase. And at the last, we will design the data structure of each and every module and the algorithm for individual modules. So first our task is to find out all the modules, then the relationship among the modules, then the interface among the modules, and then the data structure of individual modules, and then the algorithm of the individual modules. So these are the steps of this design phase. So what is a module? A module consists of several functions and it associated with some data structure. A module consists of several functions with associated with some data structure. So it is like all the functions are all the similar type functions are accumulated into a module, and those functions works on some data. Those data are to be associated with within that module. Okay, so this is called module, and this is the module structure. Here module 1 M1 this is the primary module. This module controls these two modules, and this M2 module controls these three modules. So this is the hierarchical structure of this module. And okay, I will stop it to later. So first, this is the module structure. That means you have to divide all the modules clearly and the relationship between the modules. This is the high level design. And then after creating this type of structure or modules, then we will go for the next step. That is the design steps, detailed design. So the design activities are usually classified into two stages: preliminary or high level design and detailed design. Okay, the high level design means to identification all the different modules. First you have to identify all the different modules, then you have to identify the control relationships among the modules. What are the relations between these modules? You have to find out next. And last, you have to design the definitions of interfaces among them. Okay, so first we have to find out the modules, then the relationship among the modules, and then we have to define the interfaces among the modules. So the outcome of the high level design we called the program structure or software architecture. So this is here the software architecture. So this is the outcome of high level design. That is the first part of the design phase, system design, software design phase. A tree-like diagram, that is called the structure chart, used to represent the control hierarchy in a high-level design. In this high-level design, a tree-like structure that we are finding here are called the high-level design or structure chart should be used to define this high-level design. The outcome of high-level design is the program structure, also called software architecture. Several notations are available to represent high-level design, but usually we use tree-like diagram called the structure chart, that is we have used here. There are other notations available to represent this high-level design, but here we are using the tree-like diagram. After completing the high-level design, the detailed design to be designed. During detailed design, the data structure and the algorithm of different modules are designed. The outcome of this detailed design stage is usually known as the module specification document. The outcome of this detailed design is usually known as module specification document. Okay, so for each and every module, there are some data structure and there are some algorithms. So we have to define the data structure and algorithms into this detailed design. The outcome of detailed design is called the module specification, or what we have told, outcome of this module specification document. Okay. So the fundamental question is how to distinguish between good and bad design. How you will understand that which design is good and which design is bad. Unless we know what a good software design is, we cannot possibly to design the one software perfectly. So we should know how to what is the way to distinguish between a good design, which one is good design and which one is bad design. Actually, there is no unique way to design a software. Some person may design the software in one way, someone may design in another way. There is no problem. Even while using the same design methodology, different engineers can arrive at very different design with some different design, and it need to determine which is a better design. So different engineers may prepare different type of designs, but that does not mean that one engineer's design is not good and another is good, another one is good, or the both may be good, no problem. But what are the characteristics we will look after for a good design? A good design should have the characteristic, the first characteristic is correctness. First characteristic is correctness. So that is, it should implement all functionalities of the system. It should implement all the functionalities of the system. Okay, all the functionalities of the system correctly. So all the functionalities of the system should be correct, and that's why if they are correct, then it is a good design. And the next part is understandability. A design that is easy to understand is also easy to develop, is also easy to maintain, is also easy to change. Okay, otherwise the maintenance effort should be increased. So when you are going to an algorithm, and if it is a recursion, and the same problem you can use the for loop, so you should prefer the for loop, because recursion is not easily understandable to all the employees. Keep in mind that one time, sometimes the interview may ask the question that if you have recursion and you have a for loop, which one will you prefer? There are two reasons. First reason is this should not be easily understandable, and this should be easily understandable. And the another reason is from the um, memory use. Recursion uses a stack, and a lot of memory is needed if the recursion is increased a lot of calculations or iterations. But in case of for loop, a single one or two memory is enough to calculation the whole work. You may run your program and you may check that what is the total size of the memory. So these two causes we avoid recursion, and we do the task by for loop. Next, your design should be efficient, and as your design should be efficient, so that efficiency you cannot actually measure by some unit, or measure, you cannot measure some uh, other steps. So that efficiency comes from the employers or software engineers experience. Now the last one is maintainability. Your design should be easy to change. If it is easy to change, then it should be maintainable. Then it should be maintainable. Okay, so these four characteristics will help to better for your software design to good or bad design. Now, understandability of a design is a major issue. Largely determine the goodness of a design. A design that is easy to understand is also easy to maintain. A design which is easy to understand is also easy to maintain. So, to implement this understandability, we may use the modularity. When we are doing the modularity, we can use the clean composition. We can use clean composition means, suppose I am designing the module as M1, then M2, then M3. This is our high level design, M4. Okay, suppose this is a clean composition, but if we do the modules such a way, then this is not a clean composition. So you should compose your design or high level design or modularity, you should create such a way that the composition should be clean. The clean composition makes your modularity increase your modularity. Next, unless its design is easy to understand, the tremendous effort needed to maintain it. We need to tremendous effort to maintain it. If the design is not easy to understand, so to understand the design, we need more time. Now, we already know about 60% effort is spent in maintenance. In the class of SDLC, we have told that 60% effort should be spent in the maintenance activity. In software, it is not easy to understand, then the maintenance effort should increase many times. And this maintenance effort may affect to your software industry. Okay. How to improve understandability? Use consistent and meaningful names of various design components. Use consistent and meaningful name of various design components. This is the first point to use to improve the understandability. Next point is design the solution should consist of a set of well decomposed modules. That is modularity. That means what we have already told, the clean composition. Okay, this is we have already told clean composition. Different modules should be neatly arranged in a hierarchy like tree-like diagram, and that is called layering. We have already find out what is the tree-like diagram, and we will show later the layering. Modularity is a fundamental attribute of a good design. Decomposition of a problem into a clean set of modules first, then modules are almost independent of each other, and based on divide and conquer principle, you should define those modules, you should prepare those module into some smaller modules, some identical modules. That means those modules should not be dependent to other modules. So, I think the divide and conquer principle, but I am telling that it is actually, this principle actually recursively breaking down a problem into two or more sub problems of the same type until this becomes simple enough. Okay, and the solution of the sub problems are then combined to give to solve a big problem or of the original problem. This is called the divide and conquer principle. Okay, so first you decompose the problem into a clean set of modules. The modules should almost independent, almost independent, not fully independent. The fully independent modules cannot work easily. Okay, it is not possible that in a system the whole modules are independent. Okay, based on the divide and conquer principle, we will divide this module into sub-prob modules until or unless we finish until or unless the modules are simple enough. If the modules are independent, then each module can be understood separately. If a module is independent, so you can understood it separately, and as it is not dependent, then you can modify or change easily of this module, so that it reduces the complexity of your module. To understand why this is so, remember that it is a very difficult to break a bunch of sticks, but very easy to break the sticks individually. So if there is a bunch of sticks, so to break it together, it is very tough work. But if you break it individually, then it is a very easy task. So if you want to implement the whole system, that is a very complex job. But if you divide this same system into 3 or 4 parts and try to solve this each and every module, then it is a very good or easy or simple process. This is called layering. So here this layer, if we say that it is layer 0, is easily decomposed by the other layers. That means there is no relation between this layer and this layer. Only this layer calls to this layer calls to this layer, only this relation happens. But here we cannot cleanly decompose these layers. We cannot do this because this layer calls here, again this layer calls here, again this layer calls here. That means we cannot prepare the layering here. Here the layering is not possible, but here it is cleanly layered. This is called layered solution. So your modules or your higher tree level structure should be layered solution. Is it a good design? Nobody will tell that this is a good design. Though this type of design was done previously, but nowadays the software engineers are very much knowledgeable, and they could not done this type of design. Okay, because it is a hazy, we cannot know, there is no layered solution of this design. Now fan in and fan out, these two ideas helps your system for a good, understandable, neat and clean decomposition of the whole system. So what is fan in? It indicates the number of modules directly invoking a given module. It indicates the number of module directly invoking a given module. So this is the given module. This is the given module. And the number of module and this is the number of module 1, 2, 3, 4, 5, 6, 7. These 7 modules directly invoke these modules. This is called fan in. The fan in of this module is 7. The fan in of this module is 7. So that means we are reusing the code of this module. This 7 module reusing the code of this module. So the high fan in means the number becomes high. The high fan in represent the code reuse, and that is our target. Our target is to reuse a module multiple times if it is possible, so that it increase. If we do this, then the fan in concept comes here, and if the fan in increase, so that is our achievement. The next one is fan out. It is the measure of the number of modules that are directly controlled by a given module. Number of module that are directly controlled by this module: 1, 2, 3, 4, 5, 6, 7. These 7 modules are controlled by this single module. This is called fan out of this module is 7. Fan out of this module is 7. Why this is a bad idea? If sometimes this module doesn't work, then the whole system, these 7 modules will not also work. That's why it is a bad idea. A single module controls the whole thing. If that single module do not work, then the whole thing system will be smashed. Okay, so this is the fan out. So our target is high fan in and low fan out. High fan in and low fan out. So arrangement of modules in a hierarchical structure, low fan out, and the abstraction. So in technical terms, the module should display high cohesion and low coupling. High cohesion and low coupling. So cohesion and coupling, these two new concepts comes now. We will discuss it. Cohesion is a measure of functional strength of a module. Functional strength of a module. We will give the example in the next class. So now just know that the cohesion is the functional strength of a module. A cohesive module performs a single task or functions. Suppose I am saying we are preparing a module and all the printing jobs we are done into this module. All the printing jobs of our project should be maintained by this module. So this module is special, have the specialized tasks, all the printer tasks. If we have some problem in the printing, in that case we will only look to this module, that because this printing function is available into this module. So this type of functional strength of the module is called cohesion. Next one, coupling between two modules. It is a measure of degree of interdependency or interaction between two modules. Measure of degree of interdependency or interaction between the two modules. Suppose this is a module and this is a module. This module have a value f. A that value is used to here. B is equal to B plus A. That A value is used here. That means this module should pass the value of A to this module. That is called coupling. That means there are interdependency between these two modules. Okay. A module having high cohesion and low coupling is our achievement, is our target. A module having high cohesion and low coupling. Low coupling means the interdependency becomes less, and high cohesion means the module should be functionally strong. So it calls the functionally interdependent and other modules. A functional independent module needs very little help from other modules and therefore has minimal interaction with other modules. So if the module is functionally independent, then it needs very little help from other modules. And if the modules are independent and as well as the dependency, there is no relation between other modules with this module to transfer some data or etc., then no modules are interact with this module, and whereas the interaction is less, so the complexity becomes less, and it becomes the less layered solution. It tends to the layered solution also. So what are the advantage of functional independence? It is better understandability. If the module is functionally independent, that is no dependencies between these modules, then it is better understandable. But if they are coupled highly, that means there is independent, they are independent, they are independent, they are also independent. So any value changes here may affect to this module, they may affect to this module, may affect to this module, such a way so you cannot change a simple value easily if this value is related to other modules. Different modules easily understood in isolation. The modules are independent. The functional independence reduce error propagation. Functional independence reduce error propagation. That is, the degree of interaction between module is low. When they are functionally independent, so they are not dependent for any further functions outside of this module. So the error propagation is less. An error existing in one does not directly affect to other modules. If there is an error occurs, so this does not affect to this module. It also reuse of modules is possible. Also, if this module is independent, then you may use this type of modules but in reuse to other modules. A functionally independent module can be easily taken out and reused in a different program. Each module does some well-defined and precise function. The interfaces of a module with other module is simple and minimal. If your module is functionally independent, then you may use that module if possible to other project also. The same module you may move from here to there and it will work the same if you prepare your software such a way. Unfortunately, there are no ways to measure functional independence. To quantitatively measure the degree of the cohesion and coupling, there is no way, and at least classification of different kinds of cohesion and coupling is available. So we have no way of quantitatively measure the degree of cohesion and coupling. That means in which what is the level of cohesion, high level or low level or mid level, or coupling, what is the high level, low coupling or mid level coupling, and there is no way. And at least the classification of different kinds of cohesion and couplings are also available. We will show this into our next class. So the classification of cohesion and coupling. So thank you very much.